In this video, we will be looking at section 3.7, which covers rational functions. We're going to start by looking at vertical and horizontal asymptotes. A vertical asymptote is a vertical line, and remember that vertical lines have the equations in the form x equals a constant. So we'll see that this vertical line has an equation x equals a. It is where the graph tends toward positive or negative infinity as the inputs approach a. In symbols, we would say as x approaches a, f of x approaches positive or negative infinity. A horizontal asymptote is a horizontal line of the form y equals b, where the graph approaches the line as the inputs get large. In symbols, we would say as x goes to positive or negative infinity, f of x goes towards b. So here we have a graph, and we're going to see if we can identify the horizontal and vertical asymptotes if there are any. I'm going to start with the vertical asymptotes. So vertical asymptotes mean that the function values or the y values are going towards positive or negative infinity. Well, I notice that I'm going towards positive infinity as I get really close to this line from the left. And on the right-hand side, they're going towards negative infinity. So this one is going to be a vertical asymptote. And that line is y equals x equals -1. This vertical line here, x equals 2, has function values going toward positive infinity on both sides. So this is going to be a vertical asymptote, and that is x equals 2. Now for the horizontal asymptote, we want to know as we go really super far to the left and really super far to the right, what horizontal line are we getting close to? Well, it kind of looks like we're leveling off right at this horizontal line here. Because as we go really far to either the left or right, we're getting really, really close to that line. And the equation of that line is y equals 2. When we're trying to focus on rational functions, and what a rational function is a function that can be written as the ratio, or you can think fraction, of two polynomials, p of x and q of x. So if we have two polynomials, p of x and q of x, and you stack them in a fraction, then you're going to have this rational function. Now, the way this is set up, that's going to allow us to find our asymptotes. So we're going to start by finding vertical asymptotes. Vertical asymptotes, remember, those are the vertical lines where our function values go toward positive or negative infinity on either side. So these vertical asymptotes of a rational function occur where the denominator of the function is equal to 0 and the numerator is not equal to 0. So what we're going to do is we're going to figure out what values are going to make the denominator equal to 0, and those could be our vertical asymptotes. However, if we have the case where both the numerator and denominator are equal to 0, then we get what's called a hole. And this hole occurs in the graph of a rational function if an input causes both the numerator and denominator to be 0. So if there's a value of x that would make both the numerator and the denominator equal to 0, that's just going to be a hole in the graph. So using this knowledge, we're going to see if we can find some vertical asymptotes. So first up, we have f of x equals 5 over x plus 1 quantity squared. So to find vertical asymptotes, we want to figure out where is the denominator equal to 0. So if x plus 1 squared is equal to 0, then I can take the square root of both sides, and x plus 1 is equal to 0, giving me x equals -1. Now I need to check. If I plug in x equals -1 into the numerator, am I going to get 0 in the numerator? Well, no, because the numerator is 5, and 5 is not 0. So since x equals -1 would not make the numerator equal to 0, then x equals -1 is going to be our vertical asymptote. Next up, we're looking at g of x. G of x is equal to 5 minus x over 2x squared plus 7x plus 3. I am going to take that denominator and set it equal to 0. So 2x squared plus 7x plus 3 is equal to 0. And I could either factor that or use the quadratic formula. I will factor this and I'll use the Lizzie method. So for the Lizzie method, I set up two binomials with x's out front. I need two numbers that multiply to give me 6, but add to give me 7. That would be a positive 6 and a positive 1. But I have to divide those both by the a value. 6 over 2 reduces to 3, so I have x plus 3. The second part doesn't reduce, so we have x plus 1/2. And then if we have any denominators remaining, like we do in the 1/2, we slide them in front of the x. So this factors into x plus 3 times 2x plus 1, and we want that to be equal to 0. If x plus 3 is equal to 0, then we get x is equal to -3. And if 2x plus 1 equals 0, we get x is equal to a -1/2. If I plug those in for x, neither of them is going to give me a 0 in the denominator, so these are both vertical asymptotes. Finally, we're looking at x squared minus x minus 6 over x squared minus 4. I want to take that denominator and set it equal to 0. If x squared minus 4 equals 0, that factors into x plus 2 times x minus 2. So x is equal to 2 or -2. So now I need to check to see if either of them would make the numerator equal to 0. So I'm just going to use my handy-dandy calculator. So I'll plug in 2 first. 2 squared minus 2 minus 6 is -4, that's okay. -2 squared minus -2 minus 6 is equal to 0. That's the case we don't want. So if we try plugging in -2, then our numerator becomes 0, too. So that is not a vertical asymptote, that is a hole. So our only vertical asymptote is at x equals 2. So now that we've taken a look at vertical asymptotes, we're going to try our hand at finding horizontal asymptotes. So the horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. So remember, degree means the highest power on x. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at y equals 0. And then if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote occurs at y equals the ratio of the leading coefficients. I apologize for the terrible lighting. So if the numerator has a greater degree, then there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, it's at y equals 0. And if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote can be found by taking the ratio of the leading coefficients. So here we have a couple examples. First up, we have f of x equals 2x squared plus 7x minus 15 over 3x squared minus 14x plus 15. We only are looking at the degrees, so the highest power on x in both the numerator and denominator. They are both x squareds, so the horizontal asymptote is at y equals, and then take the leading coefficients. In the numerator, the leading coefficient is 2. In the denominator, the leading coefficient is 3. So y equals 2/3 would be our horizontal asymptote. For the second one, g of x, we're looking at 2x cubed plus x squared plus x over x squared plus x plus 1. The degree in the numerator is 3, and the degree in the denominator is 2. So that's the case where the numerator has a higher degree, so there is no horizontal asymptote. Finally, for the third one, we're looking at x squared plus 2x minus 3 over 3x cubed minus 2x plus 1. Because the denominator has a higher degree, then our horizontal asymptote is at y equals 0. We don't care about the ratio if the denominator has the higher degree, it's just y equals 0. Now you'll notice that with this g of x, the second example, we didn't have a horizontal asymptote, but that doesn't mean that we don't know what's going on in the long run, going to the left and to the right of the function. It's actually a different type of asymptote, and it's called an oblique or a slant asymptote. It occurs in rational functions when the degree of the numerator is just 1 larger than the degree of the denominator. So if you're looking at the degrees and the numerator's degree is just 1 larger than the denominator, then that's going to be an oblique asymptote. To find the equation of an oblique asymptote, you can perform long division or synthetic division between the polynomials. And then the quotient will be the oblique asymptote and will describe the asymptotic behavior of the function. So when you do your polynomial long division or your synthetic division, ignore the remainder, but the actual quotient itself is going to be the equation for the oblique asymptote. So it says find the oblique asymptotes for the rational functions. And boy, that lighting is terrible. Let's see if I can make that any better. Not really. Oh, we're going to try it. Actually, I think that's worse. Let's try backwards. That's better. So first up we have 2x squared plus 3x minus 8 over x minus 1. This is going to have an oblique asymptote because the numerator's degree is 2 and the denominator's degree is 1. So we can use either synthetic division or polynomial long division to find the oblique asymptote. I like synthetic division better because it's easier, so I'm going to use that. If we're dividing by x minus 1, then I need to put 1 in my box. My coefficients are 2, 3, and negative 8. So I would have 2 multiply gives me 2, adding gives me 5, multiplying gives me 5, adding gives me negative 3. That negative 3 is the remainder, and we don't care about it. The 5 is our constant, and the 2 is our x term. So our oblique asymptote would be given by y equals 2x plus 5. For g of x, we're looking at 2x cubed plus x squared plus x over x squared plus x plus 1. This is also going to have an oblique asymptote because the degree of the numerator is 1 greater than the degree of the denominator. But this time, I'm not dividing by a linear term, x minus something. It's a quadratic. So I'm going to have to do polynomial long division. So let's see if we can get a look at what's going on. And that ruined that. Okay. Try again. Okay. So we're going to take 2x cubed plus x squared plus x, and then I'm going to put a plus 0 as a placeholder for my constant. And then I'm dividing that by x squared plus x plus 1. That is just awful. So I'm going to start by asking myself, x squared times what gives me 2x cubed? That's going to be 2x. And then I multiply this by what I have out front. So 2x times x squared is 2x cubed. 2x times x is 2x squared. 2x times 1 is 2x. I have to be sure to subtract that whole thing away. The x cubes cancel. X squared minus 2x squared is a negative x squared. X minus 2x is a negative x, and I can bring down the plus 0. I can ask myself x squared times what gives me a negative x squared? That's a negative 1. So if I multiply my x squared plus x plus 1 by negative 1, I'm going to get a negative x squared minus x minus 1, and I want to subtract that away. The x squareds cancel, negative x plus x is 0, 0 minus a negative 1 gives me a remainder of 1. But I don't care about the remainder. I just care about the quotient. So the oblique asymptote would be y equals 2x minus 1. So now we're going to try to put all of the asymptotes together, our vertical, our horizontal, and our oblique. So first up we have f of x is equal to x squared plus x minus 3 over x minus 1 squared times x plus 1. And I will figure this out eventually. Maybe. Let's see if we can hold it there for now. So we have f of x is equal to x squared times x minus 3 over x minus 1 squared times x plus 1. I'm going to start with my vertical asymptotes because those ones tend to be a little bit easier. For vertical asymptotes, we set the denominator equal to 0. So x minus 1 squared times x plus 1 is equal to 0. If x minus 1 equals 0, then we get x equals positive 1. If x plus 1 equals 0, then x equals negative 1. If I plug either of these values into the numerator, they're not going to be 0, so they are both vertical asymptotes. Next, we're going to check the horizontal and oblique asymptotes. Then we need to look at the degree of the numerator and the degree of the denominator. So we only care about the degrees, and degrees come from leading terms. So if I look at the leading terms of the numerator, I get x times x, which is x squared. So the degrees, there's a 2 in the numerator. Here we get x squared times x, so that would be a degree of 3 in the denominator. If the degree of the denominator is greater than our horizontal asymptote, is at y equals 0. So again, we're looking at the degrees, and because the degree of the denominator is greater than the degree of the numerator, we have a horizontal asymptote, and that is at y equals 0. Next up, we're looking at g of x equals 2x squared minus 3x minus 20 over x minus 5. We'll start with our vertical asymptote. We set the denominator equal to 0. X minus 5 equals 0, so x equals 5. We need to make sure that's not going to make the numerator equal to 0, so let's try plugging it in. We have 2 times 5, move that out of the way, 2 times 5 squared minus 3 times 5 minus 20. That's not 0, so sure enough, x equals 5 is a vertical asymptote. Looking at the degrees of the numerator over the denominator, the degree of the numerator is 2, the degree of the denominator is 1, so the degree of the numerator is 1 greater. That's when we have an oblique asymptote. To find the oblique asymptote, we can use synthetic division or polynomial long division. Since the denominator just has a degree of 1, I'm going to use synthetic division. I'm going to put 5 in my box, and then my coefficients are 2, negative 3, and negative 20. Bring down the 2. Multiply gives me 10. Adding gives me 7. Multiplying gives me 35. Gives me 15. 15 is my remainder. I don't care about that. 7 is my constant. 2 is my x. So my oblique asymptote is at y equals 2x plus 7. Next up, we're going to take a look at intercepts of rational functions. So we're thinking x-intercepts and y-intercepts. So we're going to find the intercepts of f of x equals x plus 2 squared times x minus 3 over x plus 5 times x plus 3 times x minus 1. We're going to find our x and y intercepts like we always do. Let's start with our x-intercepts. X-intercepts, to find them, we let y be equal to 0. So I'm going to replace f of x with 0. We get 0 is equal to x plus 2 squared times x minus 3 over x plus 5 times x plus 3 times x minus 1. If I put the 0 over 1, I can cross multiply. I get 0 times this stuff, which is 0, is equal to 1 times this numerator, which is just that numerator, x plus 2 squared times x minus 3. Well, x plus 2 squared is equal to 0 if x equals negative 2. X minus 3 is equal to 0 if x equals 3. So our x-intercepts are going to be at x equals negative 2, y equals 0, and at x equals 3, y equals 0. You may notice that this is the exact same as setting our numerator equal to 0, because a fraction can only be 0 if the numerator is 0. We can't divide by 0, so a denominator being 0 doesn't help us. But to find the x-intercepts, we can set the numerator equal to 0. To find the y-intercept, we have to let x be equal to 0. So we would be finding f of 0. That's equal to 0 plus 2 squared times 0 minus 3 over 0 plus 5 times 0 plus 3 times 0 minus 1. So that's 2 squared is 4. 0 minus 3 is negative 3. Denominator is 5 times 3 times negative 1. So that's negative 12 over negative 15, which is 4/5. So when x is 0, y is 4/5. Our y-intercept is at 0, 4/5. Now we're going to start taking a look at graphs of rational functions. And there are some things I want you to notice, some connections that we have. We said that the numerator leads us to the horizontal intercepts. That's what we just saw. The denominator leads us to vertical asymptotes. We saw that a few slides ago. Here's where things get interesting. When the degree of a factor in the denominator is odd, function values go to positive infinity on one side of the asymptote and negative infinity on the other side. So what that's saying is if your rational function is something over x plus 1, then at x equals negative 1, you're going to go towards negative infinity on one side and positive infinity on the other. Whereas if the degree of a factor in the denominator is even, so maybe if you have something over x minus 2 squared, so if the degree is even, function values both go to either positive infinity or negative infinity. So at x equals 2, they would go the same direction on both sides of the asymptote. We'll get a little bit of practice with this stuff. So let's take a look. So here we have a graph, and it wants us to notice stuff about the graph. So we're looking at the graph of f of x equals x minus 2 squared times x plus 1 over x minus 1 squared times x plus 3. Well, based on what we know, let's see what we can find. So x-intercepts. I see x-intercepts at -1 and at +2. It looks like -1, the factor that holds -1 as an x-intercept, it looks linear. Notice that that has a power of 1. It has a multiplicity of 1. Whereas at x equals 2, we kind of get that bounce back feeling. So that's quadratic, and you'll notice that that is squared. So that has a multiplicity of 2. We have a y-intercept. It looks like it happens at 1 and, I don't know, 1/4, 1 and 1/3, something like that. We could check it by plugging in 0 into the equation, but I'm just trying to observe stuff right now, so I'm not too worried about that. Let's take a look at vertical asymptotes. It looks like we're going towards positive infinity as we get close to this line on one side, but negative infinity on the other side. So our vertical asymptote at x equals -3, the infinities are opposite. One's positive infinity and one's negative infinity. That should happen if the factor that creates this vertical asymptote has an odd degree. And sure enough, it's just x plus 3. Whereas if we look at this vertical asymptote at x equals +1, it's going towards positive infinity on both sides. What that means is the term that creates this vertical asymptote should have an even degree, and it does. It's x minus 1 squared. It's also kind of hard to tell, but if we were to follow this graph out really, really far to the left and really, really far to the right, it looks like we're coming down past 2, but we're coming up towards 1 on this side. So it looks like we might have a horizontal asymptote here at y equals 1. It's hard to tell because we aren't going out far enough, but that's kind of what it looks like. Now we're going to see if we can graph one of these ourselves. So given the function f of x equals x plus 2 squared times x minus 2 over 2 times x minus 1 squared times x minus 3, use the characteristics of polynomials and rational functions to describe its behavior and sketch the function. I'm going to start with asymptotes because those usually help. Vertical asymptotes we find by setting the denominator equal to 0. So we have 2 times x minus 1 squared times x minus 3 equals 0. 2 will never equal 0. X minus 1 squared is equal to 0 if x equals +1. So that will be a vertical asymptote. And x minus 3 is equal to 0 if x equals +3. So that will be a vertical asymptote. For our horizontal or oblique asymptotes, we take a look at the degrees of the numerator and denominator. So the numerator has x squared times x, which is x cubed. The denominator has 2 times x squared times x, which is 2x cubed. Since they are the same, we have a horizontal asymptote, and that is at y equals the ratio of the leading coefficients. So this is 1x cubed over 2x cubed. So our horizontal asymptote is at y equals 1/2. So we're going to have this line here. Let's see what else we can figure out. Let's try for some intercepts. So for x-intercepts, we let y be equal to 0, and we figured out that's when the numerator is equal to 0. So if I take x plus 2 squared times x minus 2 being equal to 0, then I get x equals negative 2, and that's going to be a multiplicity of 2. And then x equals positive 2, and that'll make a multiplicity of 1. So we get negative 2 and positive 2. Those are the only places where I'm going to touch the x-axis. I should also find my y-intercept, so let's move that up so we have some room. To find our y-intercept, we let x be equal to 0, and we get f of 0 is equal to 0 plus 2 squared times 0 minus 2 all over 2 times 0 minus 1 squared times 0 minus 3. So that's going to be 2 squared is 4 times negative 2 over 2 times negative 1 squared is 1 times negative 3. Negative 8 over negative 6 is a positive 4/3. So it looks like our y-intercept is at 0, 4/3, which is 1 1/3. All right, let's see what we can do with all of this information. Taking a look at our vertical asymptotes. At x equals 1, that one was squared. That term in the denominator was squared. That means we're either going towards positive infinity on both sides or towards negative infinity on both sides. Whereas x equals positive 3, that was linear, so we either have positive infinity on one side and negative on, sorry, we do have positive infinity on one side and negative infinity on the other. We just have to figure out which. The thing is, because I have this horizontal asymptote here, I know that I'm getting really, really, really close to y equals 1/2 as I go really far out for x. So if I'm in this kind of third section here, I'm either going to approach it like this, or I'm going to approach it like this. But wait a minute, I don't have any x-intercepts over here. If I don't have any x-intercepts over here, I can't be touching the x-axis. And that would mean something like this is happening. Because I know I have to either go towards positive infinity or negative infinity. If I were going towards negative infinity, let me do this in a different color, then we'd be going towards negative infinity, but also getting really close to 1/2, I would have to cross the x-axis, and that's not happening. Okay, well, we know that x equals positive 3 has us going towards positive infinity on one side and negative infinity on the other. Well, we're already going towards positive infinity on this side. That means we're going towards negative infinity on this side. Let me erase these other purple arrows. But we also know we go through here, so something's happening here. Take a look at the multiplicity of this 0, x equals 2. At x equals positive 2, it's a multiplicity of 1, which means I'm going straight through. I can't be going towards negative infinity because I'd have to cross the x-axis again. Since I don't cross the x-axis again, I must continue up towards positive infinity. But we said we have to be going the same direction towards infinity on both sides of this line, so we have to be going towards positive infinity that way as well. If we hit the points that we know we have, take a look at the multiplicity of negative 2. That was a multiplicity of 2, so we bounce back. And then we know we level off towards that y equals 1/2. Now I know there's a lot going on here. You have a graphing calculator. Use it to your advantage. If you go into your y equals then in your numerator, be sure to put your numerator in parentheses. We have x plus 2 quantity squared times x minus 2. And then close the parentheses of the numerator. Divided by, open parentheses for your denominator, 2 times x minus 1 quantity squared times x minus 3 graph. All right, so that's not the best visual, but we are kind of getting a look at it. The vertical lines that you see are actually the vertical asymptotes. If I change my window to match what I see here, the minimum x we see is -5, the maximum x we see is 8, and it goes in increments of 1. Y min is -4, Y max is 6. Let's see if that changes things. All right, so this vertical line, we can see we have a vertical asymptote. Wow, this picture is a little bit different than ours, but we kind of guessed. We don't have to guess though. Our calculator also has a table function. If you press second, then graph, it tells you a bunch of points on the graph. So for example, at x equals -2, y is 0. At x equals -3, we should be at 0.02604. At -4, we should be at 0.06857. And you can plot all of these points. You'll notice that at x equals 1 and x equals 3, we have errors because that would involve us dividing by 0. Those are our vertical asymptotes. But if you want, you can change what this table goes by. If you go second window, you can say where you want your table to start. So I could start at -4, and instead of going up by 1, I could go up by a half. And you'll notice if I go to my table now, it goes up by halves instead of by 1. So if you want to plot by points, that's totally okay. Use your graphing calculator to your advantage. It is good. It is helpful. Let's get away from this guy. So now that we've graphed one by ourselves and we've looked at the graph of one, we're going to see what we can do about writing equations. So if a rational function has horizontal intercepts at x equals x1, x2 up to xn, and vertical asymptotes at x equals v1, v2 up to vm, then the function can be written in the form f of x equals a, which is going to be our vertical stretch factor, times x minus x1 to the p1, x minus x2 to the p2, up to x minus xn to the pn. So you'll notice this is x minus our x-intercepts raised to powers, which are our multiplicities. And then in the denominators, we have x minus v1, to the q1, x minus v2 to the q2, up through x minus vm to the qm. So that's x minus our vertical asymptote raised to a power. And we can figure out that power by looking at if the graph goes towards positive infinity or negative infinity on both sides, or if it's opposite types of infinity. So it says where the powers pi or qi on each factor can be determined by the behavior of the graph at the corresponding intercept or asymptote, and the stretch factor a can be determined given a value of the function other than the horizontal intercepts, or by the horizontal asymptote if it is non-zero. We're going to see if we can do this. We're going to start not by looking at a graph, but by looking at given information. So it wants us to write an equation of a rational function that has vertical asymptotes at x equals -2 and x equals +3, x-intercepts at -4, 0 and +1, 0, and a y-intercept at 0, 5. We don't know the multiplicities of our intercepts. We don't know what's going on either side of our vertical asymptotes. So it looks like we're lacking information, but it just says for a rational function that does this. So any function that follows these rules should be good. We're going to start off with y equals a times a fraction. In our numerator, we put x minus our x-intercepts. So x minus a -4 becomes x plus 4, and then x minus 1. In the denominator, we put x minus our vertical asymptotes. X minus a negative 2 becomes x plus 2, and then x minus 3. Now we need another point to allow us to solve for a. That's why they gave us the y-intercept. So if I plug in x equals 0, y equals 5, we get 5 equals a times the fraction, 0 plus 4 times 0 minus 1, over 0 plus 2 times 0 minus 3. So 5 is equal to a times 4 times negative 1 is negative 4, 2 times negative 3 is negative 6. So 5 equals a times negative 4/6. That means 5 is equal to, that simplifies to 2/3 a. If I divide both sides by 2/3 or multiply both sides by 3/2, I get a is equal to 15/2. If I replace my a with 15/2, then we get the function y equals 15 times x plus 4, x minus 1 over 2, x plus 2, x minus 3. So you'll notice I put the 15 in the numerator and the 2 in the denominator. Oops, last one. We have a picture, and we want to see if we can write an equation for the function based on the picture. So we know we can do it if we're given the information. Now we have to see if we can pull that information from the graph. So some information that we need were the vertical intercepts, the x-intercepts, the y-intercept, and the vertical asymptotes. That's what I was trying to say. So we have an x-intercept at x equals 2, but notice that it kind of bounces back, so it looks like this has a multiplicity of 2. So we'll have y equals a times a fraction. In our numerator, we'll have x minus 2, but since it has a multiplicity of 2, we'll square it. For our vertical asymptotes, we have one at negative 2 and one at 4. So we'll have x plus 2 and x minus 4 in our denominator. What we have to be careful of is the multiplicities on these factors in the denominator. We're going to let them be 1 if we go towards positive infinity on one side and negative infinity on the other. We're going to let the power be 2 if they go in the same direction. So it looks like they go towards opposite infinities at negative 2. That means we need to have an odd power, so we can use 1. Whereas at x equals 4, they both go towards positive infinity, and if they go to the same infinity, we need to square it. The last thing we need to do is solve for a, so we need another point on the graph. This graph isn't exactly the best, so I'm going to just kind of take a guess and say that our y-intercept is at 0, 1/2, and we will try to work it out from there. So that would be 1/2 is equal to a times the fraction, 0 minus 2 squared, over 0 plus 2 times 0 minus 4 squared. So 1/2 is equal to a times negative 2 squared is positive 4, and 2 times 16 is 32. So that means 1/2 is equal to 1/8 a. And if I divide both sides by 1/8 or multiply both sides by 8, I get a equals 4. Now that I know what a is, I can replace it. And we get the equation y equals 4 times x minus 2 squared over x plus 2 times x minus 4 squared. And there we have our rational function.